And also, I should make a confession. I'm a recovering non-holographer. And I come to these meetings as part of my 12-step process towards eventually getting into it, I hope. And so I have a few things to say. But maybe the motivation of how I got into these questions is perhaps the use or abuse from kind of my point of view of ADS in ADS CFT applications. And here, of course, I'm saying this tongue-in-cheek, but some of the questions that were in the back of my mind when I saw people giving presentations on ADS CFT is that, well, as we heard before, there are lots of things that we don't know about gravity in ADS. And therefore, I kind of had this tension of, well, how am I going to push things to try to get answers on the CFT side when, well, we still don't know, or even a few years ago, we didn't know where ADS was stable, what is the behavior of black holes perturbed in asymptotically ADS spacetime. We had questions of whether we knew all the quasi-normal modes for stationary black holes in ADS because they actually play a fundamental role in trying to understand how a CFT will relax to equilibrium. We also were wondering where, even if we knew all quasi-normal modes, where they were a basis or not, and where at least some solutions were linearized stable in the sense that we can understand the behavior of the system, at least in dynamic regimes, by just doing a linearized study. Of course, this has changed significantly, although maybe not in the direction we wanted. We now know that ADS is not stable, but there are islands of stability that have some possible interesting consequences on the ADS CFT. We know, or we don't know, where black holes are stable in asymptotically ADS, and in fact, as Gustav was mentioning, we also don't know, even in the asymptotic flat case, about the stability of Kerr. We know that we don't have all the quasi-normal modes for all relevant stationary black holes in ADS, but we're working on those. So it's a separate project. I won't have much to say about this. We know now, thanks to Warnick, that they are not a basis. So he has explicit counterexamples of quasi-normal modes not being a basis. And we also have arguments to say that the solutions in some cases are not linearized stable. And so I would have a few things to say, maybe point 1, 2, and 3, and the last one. So the word turbulence has been thrown in different contexts that we just heard in the talk by Bison and some of the questions. And I'll try to make contact with both of them. So one has come out very relevant in the context of trying to understand the behavior of pure ADS and its stability. And I'm mainly going to be picking up from the work by Bison and Rostorowski and show you some results that we have in that front. And then I'm going to move on to the behavior of perturbed black holes in ADS. And I'm going to be picking up work by all these people, but in particular some things that Van Ramstok raised a few years ago. And then we're going to try to say a few things about that. And Paul will have some very, very exciting results tomorrow to show on this. So this is like a two-part talk from that point of view. So these are some mock shots. This is related to the first question. This work in collaborations with Alex Buchel and Steve Liebling, given that these are a very heterogeneous community, so you may not know either of these colleagues. And the question that we were trying to raise and try to answer is where thermalization always takes place in pure ADS. Again, this is motivated by the work of Bison and Rostorowski. We wanted to try to understand what's the mechanism toward thermalizations that the system will show, and where this turbulence, as Piotr was discussing, play any role, and what's the role that it has in channeling this thermalization. But we wanted to add a twist to their work. It's, well, we now wanted to consider a case that will have a global conserved charge in addition to the mass, and whether the existence of this global conserved charge had anything to say about the thermalization process. So we take essentially a page from their papers, except that we're going to look for a slightly different Lagrangian, and we're going to introduce, rather than treating a real scalar field, we're going to consider a complex scalar field. That will allow us to construct this configurations that are known as boson stars, which are time-dependent from the point of view of the scalar field, but they are completely independent of time from the point of view of what their influence to the space-time metric is. So this is a work that I thought Piotr was going to discuss, but I think Andre, you're going to talk about this. So this is kind of very, very interesting work. So I'm just going to say just a few words here. So they started the problem essentially similar to that of Chopwick in asymptotic flat spacetimes, but here they do it on the ADS case. They take a real scalar field and they just ask the question: can you arbitrarily tune down the energy of the system? And if you wait long enough, the system, well, if the initial perturbation is sufficiently strong, as it collapses toward the origin, it forms a black hole. You dial it down. Now it doesn't collapse to a black hole. It bounces back. It goes away, but now bounces off the boundary. It comes back. And what they see is that after sufficient number of bounces, eventually you form a black hole. So that was at first sight very puzzling. Why is it that this scalar field wants to form a black hole after, say, n number of bounces when it didn't want to do after 1 or 2? So we had, this is a sufficiently simple context that we wanted to have some simple kind of explanation. And last year, in another of these meetings we go to as a part of this 12-step process, we were talking with Gary and Franz. And then when a very simple picture came out, we said, well, maybe as the scalar field collapses towards or compresses near the origin, it sees its self-gravity. That helps it to push it higher in frequencies. And then eventually this just keeps going until you end up localizing sufficient amount of energy in a sufficiently small region, and you have a black hole that forms. Of course, when Bison and Rosterowski came with this interesting result, I heard my field theory friends say this result is completely obvious. From the ADS CFT, you put the gas in a box, you wait long enough, the system will just explore all possible configurations. One of them will correspond to a black hole. It will stay there. There is nothing else you could do. Okay, that's an interesting thing. I'm going to come back to that later. So one interpretation, kind of from the mathematical point of view, is this resonance picture that Piotr already alluded to, and we'll hear more from Rosterowski. And this is the idea that if you have a initial configuration of energy, there is this basis of oscillons that you can introduce into space-time and expand that initial data with respect to them. And you notice that there is this resonance where if you had, say, the initial data containing three particular frequencies, they can induce a fourth one and just keep going until eventually you go to sufficiently high frequencies that you form a black hole. Interestingly enough, this is work also related by work by the Santa Barbara group, Jorge Santos, Oscar Diaz, and Gary Horowitz. They also just show that you can shift frequencies always, such that to remove the growth, but if you don't have all the higher frequencies, at some point that shift cannot be made, and then you have no way out but to just keep going and propagating that energy to higher frequencies and the black hole form. So another interpretation of that is to say, well, you're always going to have this growth if your initial configuration is such that it does not populate all possible oscillons, because in that case you are not going to be able to, by doing a frequency shift, remove the growth at least at the third order. And so this is possibly one explanation of what we see. So let me just explain what we do and then discuss the results. So we're going to construct these boson stars in ADS. As I said, it's a complex scalar field, so we choose this should be an I here, phi1 plus I phi2, described by this relation. So the real and imaginary part are given by just the simple relation. You look for solutions that are stationary as far as the metric part is concerned. You find an ODE system that you have to solve for determining the solutions, and there is a whole bunch of them labeled by a frequency omega j, which is the one you're sticking there. And of course, as I said, you have in this case charge and mass being constant. So you find as many as you want from them, and then you can then just take any one, and these are just the first 3 or 4 examples. you can decompose them back in the oscillon basis, as I said before, and you notice that you're populating arbitrary modes. So all of the oscillon, all the members of the oscillon basis come in to actually represent any of these boson stars. So in principle, you can do the shifting and remove the growth or at the linear level in time. And this is for d equal 4, so you have a polynomial decay of the coefficients in the oscillon basis. In higher dimensions, it's exponential, but it still is the case. You need an infinite number of them to represent these stars. So now let's see what happens when you actually put them in the numerical simulation and see what the evolution is. So we're going to consider several cases. First, these boson stars, and we're going to perturb them, and perturb them very strongly. In fact, we're going to perturb it in some cases with an amount of energy that is equivalent to about a third of the energy that the single unperturbed boson star has. Because of the result we see here, we're also going to consider something we call fake boson stars. So we're just going to take the boson stars from here, and in white, we're going to kill the imaginary part of one and the real part of the other one. So the excuse here is we don't want, in this case, to have an extra conserved global charge to see if there is a difference between the behavior of these ones and that one. And we're also going to take the same initial data considered by Bison and Rostorowski, and we're just going to ask what happens if you increase the width some. Again, this is motivated by the results we see from the previous cases. And lo and behold, we find something very interesting. If you perturb the boson stars sufficiently strongly, the same behavior happens. The system oscillates, it bounces several times, but eventually you form a black hole. So this is a plot of the logarithmic time at which the collapse of a black hole forms versus the amplitude of the initial perturbation. And you keep dialing down, it takes more and more time, but then at some point a significant change in the trend is observed. It's no longer monotonic, and then it just seems to shoot up to infinity. Well, and so this would indicate that these stars are stable. So if you don't perturb them very strongly, then the space-time seems to be very happy to stay in one of these stable, in one of these boson star configurations in an apparently stable manner. And there is no difference whatsoever, qualitatively speaking, in the behavior of these real boson stars with respect to these fake boson stars. So this question that maybe the behavior of the system being stable or apparently stable being tied to an additional conserved charge in the system, that cannot be the answer because the fake boson stars do not have it, and yet they show the same kind of behavior. So then, motivated by that, this is what we said, well, let's just go back to Bison and Rostorowski data and consider a larger width. And again, we found that same behavior. So again, for sufficiently small width on the initial configuration of the data, you have the same behavior that they found, as Bison was referring to. But you make the width slightly larger, and again, there is a marked transition, and then the time to collapse just shoot off to infinity as far as how long we can run our simulations. And then follow-up work, they actually even increase further the width, and they find again that the collapse takes place for arbitrarily small amount of perturbation, so this is a very kind of puzzling observation. The system seems to want to either go and form a black hole for arbitrary small energies or not. And so then the observation is that we now have several cases that appear to be pointing to ADS having this islands of stability. And these are either boson stars, geons, as the Santa Barbara group has created, some other family of solutions that Maliborski and Rostorowski have constructed, which is kind of, at least it's thought-provoking. So what all these works are pointing to is that black hole formation is not guaranteed, which then kind of reminds me of this initial field theory friend's statement that this result of collapse of a black hole was completely obvious. So where did that go? We start in all cases with a small amount of energy in ADS, and the system seems to have at least some ways to not want to collapse to a black hole. Of course, these authors claim or have an argument for that. They say, well, this is because one is doing an infinite n limit, and one is not accounted for quantum gravity corrections. If those were accounted for, the system will actually have no problem in tunneling into a black hole configuration. But it still is puzzling that we have, perhaps the one that I find it the cutest is this example of Wison and Rostorowski data. You just choose an initial configuration with a given width. It has no problem forming a black hole with an arbitrarily small amount of energy. You make it slightly wider. It doesn't want to form a black hole. You make it even wider, and it wants to form a black hole again. I think we need, at least from my point of view, I'm not too happy with all the with the understanding there. And it's also this simple gravitating argument, this thing that as this configuration of energy converges towards the origin, it itself pushes to a higher frequency and eventually does it so in a way that will form a black hole. Of course, it isn't quite correct. So the way we understand the behavior is kind of saying there is a tension in the system where there is a tendency towards collapse, but there is a competition towards dispersion. And so we want to understand where that picture makes sense, and we're doing follow-up work on this. And of course, the question, and this is similar to Bison stuff, is just a question I throw in. Well, what is this consequence for thermalization, and why, who ordered this kind of complicated behavior that we're seeing? So I'll just leave this question there and then completely change gears. So this is now a different kind of application, and this is towards question number 2. And I'm interested here in how do perturbations of black holes behave in ADS. And so again, these are the Max shots, and this is a student, Federico Carrasco in Argentina, Ajay Singh, another student in Perimeter, Stephen Green, a postdoc, and Rob Myers, and this is Oscar Reula, also a colleague in Argentina. So while I want to understand the behavior of black holes, perturbed black holes in ADS, I'll try to simplify the problem and also the coding that it goes with it. And I'll just look for perturbations in a very particular kind of corner of the parameter space. And I'm going to consider perturbations that satisfy the relation, this relation, that the wavelength of the perturbations I'll consider times the temperature of the black hole is much larger than 1. I'm going to do that because I can use the ADS CFT correspondence, as people have done in the past, to then motivate looking for a fluid gravity correspondence, and then just say I'm going to study the black hole spacetimes, not on the gravity side, but on the hydrodynamic side. And the interesting observation is that once I do that, and if I'm staying at this limit, I have to remember that turbulence might come in. And if I ask what this limit may imply for turbulence actually happening or not, I have to remember, at least in the regime of the non-relativistic hydrodynamics, that there is this quantity called the Reynolds numbers, which is kind of the ratio between the density of the fluid divided by its viscosity times the velocity of any particular characteristic perturbation times the wavelength that that perturbation has, much larger than 1. Of course, rho it scales like temperature in the ADS CFT. Rho scales as t to the d. Eta the scales as t to the d minus 1. So this ratio is precisely t. The velocity is bounded by 1, so I'm going to throw it away. And what I have here is t times L, much larger than 1. So at least from that point of view, turbulence should be prevalent or very possible. And I'm going to have to live with that. And so this is an interesting observation, that the hydrodynamic behavior is already telling us that turbulence might happen. But then this is in kind of stark conflict or tension with the standard law of black holes perturbed, just decaying away via quasi-null modes. But as I said before, there is this caveat. We also already know that quasi-null modes are not a basis, so maybe there is a corner of the parameter space where a given perturbation will trigger something else in a quasi-normal mode. So I want to make contact with those and see where things take us. So as I said, the ADS CFT motivated looking for a gravity fluid correspondence, and this has been shown by these authors, many of them being here in the audience. So the context I'm going to study, or going to show some results, is perturbations of a boosted black membrane, but it shows you also some results in the global ADS point of view by studying the dual perturbations to Schwarzschild and Kerr black holes. So in this context, if one introduces these metrics and allow these otherwise constant functions to depend on space, one can stick that into Einstein's equations and solve order by order in a gradient expansion, and then realize that when one projects the Einstein's equations on a particular time-like surface, and in particular the ADS boundary, then one induces equations that are completely equivalent to that of a fluid that is a relativistic fluid that has these stress energy tensor associated to it. It satisfies these conditions, particularly it has to be traceless due to conformal symmetries, and then there is a higher order terms to the perfect fluid contribution that involve dissipation, and this dissipation is directly linked to the fact that gravitational waves will be lost into the black hole. So one, again, just to stress the point, one might want to wonder where these equations and these particular equations say give rise to turbulence. After all, much of what we know of turbulence, which is always very little, we know typically in the non-relativistic limit and for equation of states that are not as special as the one that come from this condition, rho divided by the spatial dimensions. But of course, if we remember that the non-relativistic limit of these equations give Navier-Stokes, it would be very surprising if we don't have turbulence in this case. But also, we do know that in the case of the Navier-Stokes, we have very different behavior in turbulence, where we're in 2+1 dimensions or above. This is because in 2+1 dimensions, there is a conserved quantity, which some very perturbed individual call it entropy. But this is, again, not necessarily for the relativistic case. So it was a question where this exists for the equations, for this equation and this equation, these relativistic equations and this equation of state. Again, I should remind you of what the behavior uncovered by Bison and Roskorowski is. It told us that these weak turbulence which tend to send energy into higher and higher frequency modes regardless of the dimensions. If we actually have an inverse cascade in 2+1, it would be telling us that there is another phenomenon that actually wants to send energy into shorter and shorter frequencies, which would be interesting on its own sake. So the first thing we did is just to go and try to find where there is this entropy for the relativistic case, and just as a reminder, in the Navier-Stokes case, the vorticity is defined very simply like that, and this quantity entropy is defined as the integral of the vorticity square, and it's conserved if there is no viscosity. So for a relativistic hydro, one can go through the motion and actually find out that there is indeed a current that is conserved that can be constructed this way, with this omega just being kind of an analog of the vorticity that is one throws in the density there. And eventually, the quantity is conserved, which this entropy is given by this, which is it's very similar to the one has in the Navier-Stokes case. It has the square of the vorticity, even though this vorticity has, this vorticity is exactly the same as before, sorry. And it has a contribution of the acceleration, because now fluid lines are not necessarily geodesics, and a Lorentz factor. But aside from that, everything goes and so the same, and so we expect that turbulence will actually cascade in the opposite direction in the 2+1 dimensional case.
Why is this special in 2+1?
This is especially because there is an equation. The Navier-Stokes, the understanding Navier-Stokes is that this, because of the same thing. So you can understand that the rate of change of the energy is tied to the viscosity. It's tied to the entropy. The fact that the entropy is conserved is telling you that there is a bound in which, as to how the energy can change. And they cannot, if you take the limit to the viscous scale, it tells you that both of them cannot be going in the same direction. One has to go in the opposite. So it goes, the analysis goes in exactly the same ways in the Navier-Stokes case.
But you still have to assume that the viscosity is 0 for this to be conserved?
Yes. For it to be conserved, the viscosity has to be 0. And we can always remember that the viscosity is sub-leading in the temperature, so I can always play the game of going to sufficiently high temperatures to say, well, I can make contact with this observation.
Sorry, I'm a bit confused. Isn't the entropy conserved even with non-zero viscosity in a non-relativistic case?
No, it's not. So no, the entropy, if you have, there is a rate of change of the entropy as well, which is proportional to the viscosity. One might wonder, well, what happens in the bulk? Okay, so the duality, this fluid gravity duality, it also tells us what the metric is all through the bulk, and it has really a trivial extension to it. There is no extra dependence that is built in the orthogonal directions to the radial direction, so you expect everything to go the same. So you actually can repeat the steps, and given that you choose particularly well-defined time-like surfaces inside, which is always a question mark, because well, who gets to decide what those surfaces are? But if we agree that a good definition, provided that our initial perturbation is sufficiently weak, is those time-like surfaces defined by the unperturbed metric R equal constant, then you can go through the motions and get exactly the same thing. You get relativistic hydro, you get now an equation of motion that is not exactly conformal, an equation of state that is not exactly conformal, but it obeys a relatively simple relation. And you can also derive an entropy. So again, in the bulk, at least from this point of view, choosing those particular time-like surfaces, you also would conclude that the same behavior will happen, in that you have a conserved entropy, and therefore you expect the inverse cascade. And of course, this is trivial. It's a trivial expectation just by the fact that the extension into the boundary is relatively trivial. So I'll show you some results now. I'm going to concentrate mainly on what happens to a dual to a black hole in a Poincare patch, or a black membrane, and also show you some examples on the global ADS. Of course, we're going to do numerical simulations in 2+1 dimensions, because 3+1 are tougher. But we can already, when we see from here, we can speculate what's going to happen in the 3+1 case. And there is some work on the 3+1 that also supports our conclusions. I'm going to choose either a flat topology. Actually, and for simplicity, I'm going to use a torus, or S2 to make contact with the first case or the second. So this is, let me just play this movie. So here what we're doing is choosing initial data, again, on a torus that describe a particular configuration of, say, the velocity in the x direction being either a constant or zero, it doesn't matter, with a given perturbation in the orthogonal direction. So we're actually turning on the shear mode of the fluid, and we're just going to let it go. And because it's the cleanest thing to show is the vorticity, this is what I'm going to be showing, and these are just some snapshots of the evolution. So you'll see what happens, and you may see something very similar tomorrow in Paul's talk. So after a while, then you get all sort of vortices going around, and then you begin to see that the vortices get larger and larger, and if you keep looking, then at some point you get to a configuration where you have the largest possible vortices that you can support, given the torus side that you have chosen. And we already know from the Navier-Stokes results that equal sign vortices can join, opposite sign vortices will repel, and equal sign vortices will join only if they are below some minimum distance. Above that, they just stay happily in their own, but because the motion is completely, and it's very chaotic, eventually they find themselves, and then they begin to merge. And if you wait long enough, now the velocity has gone sufficiently low, the velocity of the fluid is decaying all the way because of the viscosity. These vortices are well approximated by something called the Auchin's vortex, and there's a nice, interesting paper by Gallay and Wayne that prove that these vortices are stable and are attractor for Navier-Stokes solutions in 2+1 dimensions. And again, this is what you extract, and is precisely what the theorem tells you. So now we can say, well, how does that is seen in the bulk? Of course, we saw that vorticity plays a key role. At the end of the day, we have a bunch of vortices going around, and it's encoded everywhere. So depending on who the authors are, they get to pick whatever they prefer. So These authors choose the Pontryagin density, and the reason for that is to observe that the vorticity is a pseudo vector, so let's construct a pseudo vector from that, and then that's a very natural condition. Epstein and Oz choose to look at the imaginary part of psi2 being the Newman-Penrose Bayes combination, and you know that has to do with the mass aspect of the system, and when you project it onto the horizon, what you get in the imaginary part is essentially the temperature times the vorticity. We chose to look at all of them. In particular, the one I like the most is the psi4, which tells us the gravitational waves. And so if I'm looking at the horizon, what I'm seeing is what is the role of the entropy as having gravitational waves falling into the horizon. And interestingly enough, you compute what the value of psi4, and to leading order is just purely imaginary, and that tells us there is just one polarization of the gravitational waves, as we expected, because we have a structure is essentially axisymmetric. And the structure is like, well, it's like a geon-like configuration. So you have gravitational waves that somehow have come together in a localized structure. They're sufficiently self-gravitating, not as to disperse, but it's not too self-gravitating to come and collapse on its own. And so these are just some pictures of, this is the Kretschmann invariant of the perturbed solution divided by the Kretschmann invariant of the unperturbed solution. And this is just assuming on psi4 times sin4 complex conjugate, which actually is the energy, the flux of energy of gravitational waves, related to the flux of energy of gravitational waves. And you see this kind of, in not so great plot, this kind of contained configuration of gravitational waves there, as they cross the horizon and all the way to the boundary. So you could call this gravitational wave tornadoes if you want. In global ADS, it's even more fun. I actually like this a lot more. So I've been staring at these movies for too long, so I have to explain what this is. So we're trying to do something on an S2. We cannot put a single patch on an S2, as we all know. So we're going to just put 6 so as to have the most symmetric configuration. So you have to picture this kind of in the buckyball configuration. So this is kind of the equatorial region. If you turn it around, you identify, well, you cap it with this, cap it with that at the bottom. That forms a little ball for you. So it's actually, it takes some training to actually see that this guy gets continued here, that guy is continued over there, etc. And let's see. So first I'm going to turn on a perturbation on Schwarzschild, and I'm going to keep showing you the vorticity. So let's see what happens. Again, we are in the turbulent regime. This thing should show the turbulence, and after some time, you begin to see it. Similar as before, you develop vortices of both signs. If equal sign vortices get sufficiently close, they will merge into a larger one. And we're going to end up with a particular configuration that I'll be pointing it soon. There is no net flow around. Again, this is dual to Schwarzschild, and Schwarzschild has no velocity background flow. So eventually we end up with 4. 2 of one side, 2 of the other side. And of course, the immediate question is this a complete artifact of the numerical simulation? How is it that we end up with 4? And we actually had that same thought. We tried, as much as we tried, to put initial perturbations inclined with respect to this configuration, etc. We always get this 4 in Schwarzschild.
What singled out that?
Say again?
What had singled out that direction?
This is so the particular perturbation you have. So it gives a particular preference in that direction. But now if I tilt it, then I end up with one that sits here, right? Then another one here, another one there, and another one here. So it actually gets tilted, but it's always this 4. Now it's even more fun to see. Now let's put some background flow. This is the dual to Kerr. And so initially very much the same, except that you have a net flow in a given direction. You generate a lot of vortices. We tend to join. Again, remember, we have an inverse cascade, so we want to go into higher and higher, into longer and longer wavelengths. But now we end up with 2. One ends up at the top, and the other one ends up at the bottom. And if you wanted to kind of predict where this would have ended, you could have thought of, well, let's think of Schwarzschild, perturb it a little bit, and see what would happen. And so you can imagine that if you now have a vortex, a background solution that has a velocity in, say, in that direction, you could ask, where is this going to go? And if you use Bernoulli to guide your intuition, you get the answer completely wrong. So you could say, well, if I have a velocity going in that direction from the background flow, I would have an effective velocity here that is larger than the one here. So I would have an effective pressure here that is larger, lower than the one here, and then this would have to move up. But the truth is this has to move down because the background velocity is larger at the equator than at the poles. So there's an effective larger vortex going in this direction towards the north pole, in this direction towards the south pole. So these two guys actually want to merge with that vortex and they will go down. As they go down and get sufficiently close, they merge and form a single one. And of course, these other ones do the opposite.
Here, are you solving Einstein's equation?
No, I'm solving. That is all Paul. So Paul is going to show some awesome results to point in this case, but he's doing it on the torus case. But to the extent that we believe the fluid gravity duality, and that this regime, because we started at LT much, much larger than 1, we never get out of that regime because we're going to even longer wavelengths, then this result is immediately telling us what the ADS behavior. This is relativistic hydro.
With viscosity.
With viscosity. Well, this one is not with viscosity. There is some numerical viscosity added in, but the previous one all had viscosity. We go all the way to second order in the hydrodynamic expansion. So one can ask, well, let's push this a little bit more. How much can we get out of this? So we already established a turbulence does start. Eddies merge, depending on the sign. Fully developed turbulence grows to about the initial perturbation size, and I'll say more what I mean by this in a second. The cascade to longer wavelengths happens, and if you now ask, take the energy, do a Fourier expansion, and try to see if it is consistent with the minus 5/3 Kolmogorov exponent, the answer is yes, and this is just an example of that. A caveat here is that we do not have Kolmogorov arguments in relativistic case. When you try to do a dimensional analysis, the fact that we're doing things relativistically now make us lose one particular control parameter, but for low enough velocities, we expect to make contact with the Navier-Stokes case, and okay, indeed, we get the minus 5/3. But more importantly, we actually see that once you fully develop turbulence, then there is a significant rate change in the global behavior of the system. So here I'm showing the L2 norm of the vorticity, but I could be picking any particular global norm. So initially what we did, and this I'm talking again of the torus case, we put a shear mode where it's triggering one particular quasi-nodal mode, and you expect from the linearized intuition that the black hole would just decay away exponentially with that mode, provided turbulence didn't happen. But because turbulence did happen, you see a decay, and this because it's a log-log scale, it looks kind of weird, because actually I want to concentrate more on this. So initially you see the decay that is purely exponential given by the mode you excited, but at some point, once turbulence is fully developed and you have achieved some sort of equipartition, you give rise to a power law. This power law for the vorticity obeys this behavior. So the vorticity versus time it obeys the power law of C2 minus A, and A is measured depending on which case we are looking between 0.5 to minus 1.5. And there's a theorem by Galay again and Wayne that said that the bound for the rate of decay is T to the minus 0.5. So some cases actually saturate that bound. Others have a little bit more room, but in all cases we're decaying. But it's interesting to point out this relation with Gustav's talk that there are cases where the decay rate is not too fast. So going now to this quasi-nodal modes versus hydrotension, well, in principle, there is no tension because, as I said, quasi-nodal modes, we now know they are in the basis, so maybe we're just triggering this mode that say, Claude's counterexamples. But we actually started with a quasi-nodal mode, so what's going on? Well, just as a reminder, the standard perturbation theory essentially is built in by solving order by order a perturbation theory where you say the full metric is given by some background plus some first order perturbation, etc. And you solve at every single step the box equation of the background acting on the particular order of perturbation one is interested in equal to some source that only contains previous orders. So if you analyze this equation, you will never get an exponential growth, but we actually are seeing that. And so this is actually very much akin to what we already know in the literature by the transition between laminar flow or turbulent flow, where, I mean, the key observation is what the Reynolds number is. To very, very large Reynolds number, you'll have the exponential growth. At very smaller ones, you have a laminar flow. But of course, we have to remember the Reynolds number is a function of time because the flow is decaying. The velocity is getting smaller and smaller. So these are just 3 examples of our simulations where we actually tune in either the initial wavelength of the perturbation or initial velocity of the perturbation to either have a purely laminar flow, where this is where we put the perturbation. Say we put the perturbation in the x component of the velocity. But if you monitor the y component of the velocity, that should stay 0 or very small. This one, they're both decaying with precisely the quasi-normal mode decay rate. In the other end, if you start with a very large Reynolds number, again, this is the velocity, the component, the x component of the velocity, and this is the y component of the velocity where we initially put nothing, but nonlinearities trigger this exponential growth. It gets to be of the order of the initial perturbation Vx, and this is where you reach this sort of equipartition, and turbulence is completely fully developed here. But there are intermediate cases where initially the exponential growth takes on, but as time goes by, because the velocity is getting too small, you go into the too low Reynolds number, and then it turns around. So there's these 3 phenomena are displayed there. So one can then also try to make contact with the Reynolds number. We have to remember that the Reynolds number is, again, a concept that is purely what is just decently known in the Navier-Stokes case. Here we're talking about the special relativistic, but we still try to make some contact with that. So these are some examples that we've done where you try to measure just by looking at the growth rate or the behavior of this this y component of the velocity that initially is 0 and it gets triggered by the nonlinearities, where they grow as a function of velocity. So if you crank up the velocity, so for very sufficiently small velocities, the mode just decay exponentially, but then as you increase it, at some point, it turns around, so it goes from an exponentially decaying function to an exponentially growing function. So you can see that indeed it's proportional to the velocity. You can also monitor, if you keep everything else constant and change the wavelength of the perturbation, also how it changes. And indeed, well, it's proportional to lambda, and you can even measure the coefficient in front, and it's a number of order 1. So roughly one could say that the Reynolds number in this context we can define as the temperature of the black hole, the wavelength of the perturbations times the determinant of the metric perturbation, and that seems to be a relatively good figure of merit. So I'm going to conclude with some observations. So turbulence should take place in ADS, and tomorrow we'll see some author results that say yes. And turbulent, we also know that turbulent, when turbulence happens, turbulence is self-similar. So you also expect a fractal structure, and this has been raised before, in particular by Oz, and we also will see that tomorrow. We know that the inverse cascade carries over to relativistic hydro, and so gravity in turbulence, so gravitational turbulence in 3+1 and 4+1 dimensions move in completely opposite directions, which of course has very interesting consequences. In 4+1 gravity, the cascade will be direct. We're going to generate smaller and smaller scales. As we get to sufficiently small scales that we meet the viscous scale, we're going to be dissipating them very efficiently. So one would expect the system in 4+1 to equilibrate more rapidly than that in the 3+1 case. Can we say anything about the possible Kerr instability? From the results we have, you don't expect in this regime to have Kerr be unstable. You have these perturbations that go into either longer wavelengths or shorter wavelengths, and they're always decaying. So Gustav's proposal of Kerr being unstable better happen before that. We're outside the regime of applicability of the fluid gravity correspondence. There's a warning, of course, for simulations. We know that even though we can morally be working in 4+1 gravity or above, the moment we introduce symmetries to simplify the computational codes, we can actually completely kill turbulence. An example was Franz's result. The symmetries assumed do not allow for turbulence to kick in. So that's, of course, it's very well known in astrophysics that one has to be very careful. So again, the same applies here. So kind of the final transparency, so we know quasi-normal modes are insufficient to understand relevant system, and this goes to the observation of linearization instability or stability of perturbations. We know that quasi-normal modes do not completely tell the picture because turbulence actually mixes things in, and we actually see a different time behavior showing up when turbulence actually gets induced. In 2+1 hydro, we're safe. Everything we've said would apply, because if we start in the regime of validity of the duality, we'll stay there because the inverse cascade takes us into longer wavelengths, so we keep satisfying. So the fact that Navier-Stokes are contained in the relativistic case in the low velocity regime implies, of course, that we're going to have we're going to conclude immediately that solutions are well behaved for Navier-Stokes. Of course, for special fluids, those that have this very particular equation of states. In 3+1 hydro, one can start in the domain of validity but get out just because the cascade goes into the opposite direction. However, the same thing applies that we know or from intuition in the Navier-Stokes case. If our initial wavelength is sufficiently, or is not our initial wavelength, if the viscous wave length is such that the viscous length and the temperature, which scales roughly as T to this large power, is much larger than 1, then we'll never get out of the regime of validity. So at sufficiently high temperature, the black holes, we know what's going to happen. We're going to generate smaller vortices. The vortex will hit the viscous length and then will decay away. And so establishing that solutions are well behaved mathematically on the black hole side will immediately also tell us that for these special fluids, the Navier-Stokes have well behaved solutions. And as the last kind of thought-provoking thought, one could wonder where gravity is only turbulent in ADS cases, because why is ADS special from this point of view? Well, the key physical observation is ADS has very slowly decaying modes when compared to the asymptotically flat case. So the long-term behavior of the solution is governed by these decaying modes. However, kind of in the very nonlinear regime, the one valid question is whether the shear modes are present or not. And it turns out these modes are present, and this is actually very interesting work that Jorge Santo has done in some collaboration that we have in this trying to understand the quasi-normal modes in curved black holes. And I find it particularly interesting because it means I won a bet to Vitor, so I have a Porto bottle coming my way. And the answer for that was the question, well, take the shear modes in ADS. Now take the length scales of ADS to infinity so that you make closer and closer contact to the asymptotic flat, and does that mode exist in the modes that we know of asymptotic flat black holes? And it turns out the answer is yes, and it's known as the algebraically special or Robinson-Traubmann mode. And with that, I'll conclude. Thank you.
Luis, I'm confused about your connection between Warnick's result and the hydrodynamic story. The hydrodynamic story is valid for a small class of quasi-normal modes with zero radius of convergence. It's an effective field theory, whereas Warnick's result is for the whole spectrum of quasi-normal modes. They're completely distinct objects. What was your statement about their connection?
Now, the connection that I was trying to make there was just to say, can we believe that we could represent the solutions in terms of quasi-normal modes? And from that point of view already, the question was already resolved first by Claude by saying, look, not all perturbations are describable with quasi-normal modes. That's all the connection I was making. In this case, though, the connection is, well, we've seen that some intermediate stage, when you're in the regime of fully developed turbulence, you actually have a behavior that's not in the quasi-normal mode, expectation. And it's different, and it's due to this exchange of energy in the inertial regime.
No, but if it's in hydrodynamics, it's the collective excitations of a particular class of quasi-normal mode, the hydrodynamic quasi-normal mode, what you call the slow modes.
We're talking about this is a nonlinear regime.
Well, the hydrodynamics is a nonlinear theory.
Of course, yeah. But what I'm saying is, so I could imagine that I put, and again, so I could do I could try to address that question purely on the hydrodynamic front. So I take hydro and I take an absolutely small amount of energy. I couldn't care less about how much energy I'm perturbing my solution with, but I make it with a very, very long wavelength. So one would perhaps naively expect that I didn't change things by a whole lot. I put a tiny amount of energy. But the moment I make it too long in wavelength, I get turbulence. And so now the nonlinearities quickly take me out. But I make the wavelength slightly shorter so as to be below the critical Reynolds number, and then the linear behavior is the correct one.
Just about this boson stars in ADS. Does any dependence on this conserved quantity on the charge? If you change the charge stability?
No, we don't see it playing any significant role. But initially we thought it would, but
Interesting.
I have a question. In your simulations, at the end, you have two vortices of opposite signs. If you continue this simulation for even longer times, will they merge?
no, because they are opposite signs, so they cannot merge.
No, but you mentioned the theorem by Wayne about the attractor. So
No, but the theorem by Wayne says that you're going to have a bunch of vortices. Each one of them has an attractive solution. So each individual one. So the standard kind of work of, or kind of the latest work on trying to understand turbulence concentrates on these entities and their behavior. So here you're going to have, from their point of view, each vortex is one entity that can be described that way.
I'm a bit confused about why these islands of stability would be a problem for thermalization. These are first order transitions which have a stable or metastable phase, which is just pure supergravity gas. So you can imagine forming that, and then
Yeah, I just find
at the low enough temperature, it's thermodynamically stable, or energy is thermodynamically. That's the thermodynamically preferred configuration.
Yeah, I just find it very strange that, I mean, somehow the system decides to have no problem to go and form a black hole. I put a very little amount of energy, but I never change that amount of energy, and I just make it of some given width, some larger width, and even some larger width, and I go from 1 to the R to the R1. So there is this kind of case in between that somehow has to find a way to form a black hole. These are two have no problem.
Regions of phase space, so that at some point you go to one or the other, right? I mean,
Yes, I find it puzzling the way it does, the way it behaves. But as I said, I'm not in the field theory side, so I don't have that intuition.
at low temperatures, you might complain the opposite. At low temperatures, you're thermodynamically dominated by the supergravity gas. So forming a black hole would be creating the thermodynamically not preferred state.
That never happens in the classical limit.
Yeah.
And it depends on how you scale the energy with them, I guess.
I mean, just to add on that, you wouldn't expect to form a tiny short-shelled ADS black hole, per se, because that thing is unstable anyway.
Yeah, so if they are there, you're fine, because then, okay, that tiny black hole might have time to evaporate and you can get out. But from the point of view of the classical work that we can do here, okay, that doesn't play a role.
No, I'm not even talking about the quantum aspect. If you take if you form a black hole whose energy is small in ADS units, half of the ADS size, then that thing is not even is Gregor-Laflamme unstable to in a full ADS CFT context on the 5 sphere and so forth. So already that one would be suspect from the CFT standpoint. It's not the thing that corresponds to the surface state. So you would need an excitation of energy comparable to the ADS scale to kick you into the regime where you would naturally collapse a black hole.
But those modes are not in their problem.
Collapsing the black hole.
You need the full 10-dimensional theory to see it.
They would need but
They're projected out because they're in 5-dimensional
Yeah.
geometry.
that's fair enough. But
Any other question?
So you mentioned this interesting regime where you have the Gaussian pulses and at narrow width they're sort of stable, and at intermediate width you make black holes, and at longer width they appear stable again. But in the intermediate range, where they appear to be stable in the current, where they appear to make black holes in the current simulations, they appear to be stable in the current simulations. Don't you expect that if you turn the amplitude down further, so you were truly in the perturbative regime, that they would again tend to make little black holes and exhibit instability? Or at least, don't you think this is an interesting question to explore?
Yeah, this is similar, absolutely. This is similar to the comment that Gustav made, or that you made in Gustav's talk, that, yeah, if you go all the way to very, very tiny energies, then your regime where pure ADS is unstable. And so, but then it's cute to see that, okay, in this direction it's stable, in that direction it's unstable. Yeah, I'd like to understand better. And then why is it that the system should be sufficiently simple that it should be able to come up with a kind of intuitive physical explanation for what's going on, and I don't have it. I mean, the picture of resonance is fine, but that's a mathematical explanation for me. I just want something more, a closer contact to physics.
Let's thank Luis.